this is an experimentalist point of view. And so here I'm zooming in on this image regime, which goes from maybe a few MeV up to a few tens of MeV. And it's populated also by low-end reactor neutrinos and neutrinos from the Earth, as well as solar neutrinos are out on a somewhat lower energy end of this range. And so here I'm going to talk mostly also about burst supernova neutrinos. So basically what you can see when a nearby supernova happens in the galaxy or nearby the galaxy, where you get a whole bunch of neutrinos in a burst. There's also what are called relic supernova neutrinos or diffuse background solar supernova neutrinos, which come from integrating all the supernova neutrinos emitted over the history of the universe. I'm probably not going to get to that in later. Okay, so neutrinos from quark clouds, just general physics. The general physics of this is just as you get gravitational potential energy when kinetic, you get that turned into kinetic energy and thermal energy when an object falls and crashes, just as when a star falls inwards after it runs out of fuel and collapses, and the matter has to fall inward, that energy has to go somewhere, and because that energy can escape via neutrinos, thanks to their weakly interacting nature, that's why essentially all the energy can escape, because it can escape on a timescale shorter than the other interactions. So it turns out that when you have a gravitational collapse of a star at the end of its life, it's no longer able to produce energy from fusion reactions to keep itself, to hold itself up, and it will collapse. And almost 99% of the vast binding energy of the remnant of the super ultra-dense remnant protoneutron star will be emitted within about 10 seconds or a few tenths of seconds in the form of neutrinos and antineutrinos of all flavors. And this is something, this is again a whole subfield that I'm not going to go into the details of. There's a lot of people working on the detailed simulations of the supernova, quark collapse supernova and the explosion. Explosions happen when you get a rebound from the bounce, some fraction of the time, which is not 1 and it's not 0. Sometimes you get a collapse to a black hole subsequently, and these, the numerical study of this is a whole topic. And what is known is that neutrinos are definitely part of this process, and the emission of them will tell you about what is going on. Now, this is a slide that I always need if I'm talking to astronomers. I think probably not so many of you are astronomers, but I will say this anyway. When I talk about an event in particle physics, that does not mean the whole supernova. That's what it means to astronomers, we mean the whole supernova. What I mean by an event is a single recorded neutrino interaction. The energy scales of these two kinds of events are many, many orders of magnitude different from each other. Supernova explosion is something like 10 to the 50-something ergs, whereas a single neutrino depositing energy in a detector is some tiny fraction of an erg. And so when I say things like the IMA detector saw 8 events from 1987, we're talking about one big event and lots of little ones. Okay, and so the information that you get from neutrinos is the kind of information that you get from these particles that can come from deep inside this very dense, exotic proto-neutron star object, or collapsing object. And there's enormous information, and the information we can get at experimentally is the flavor of the neutrino interaction, flavor of the neutrinos that come out, the distribution of those, their energies, so their spectrum, and how those vary in time. So the profile and flavor, energy, and time is essentially the observable that we can get at. Of course, we want to know it in fine grained detail, but in real life you have you only can do what your detectors can do for you. And so here's an example of the neutrino truth that may come out of a star. The top 3 plots, these 3 columns are 3 different time scales. This is 15 milliseconds. This is 1 second, and this is 10 seconds after the collapse of the star. The top ones are luminosity of 3 flavors of neutrinos: electron neutrinos, antineutrinos, and mu and tau neutrinos, and their antineutrinos. We'll see in a bit why only those 3 are important, that the mu's and taus are all lumped together. And so this here, you can see that in the electron flavor, it's a solid line. You get some exciting action. You get a very These bottom here, this is the average energy as a function of time. And here you can see, again, that these differ. So the features here, this turn on of electron neutrinos is the infall. This is where you're actually making a neutron star. You're getting protons and electrons that are squished together to make neutrons and emitting electron neutrinos. So that's what you start to get at infall. This little notch, the neutrinos are actually trapped for a short period of time, which is a mind-boggling concept that you have a matter that is so dense that neutrinos themselves are trapped, but then that happens for a very short period of time. You get this sharp burst. This is also called the de-electronization peak. It's electron neutrinos where you get a very bright flash of electron neutrinos in that short spike of a few tenths of milliseconds time scale. In the second block here, after about a second, you can see also shenanigans in the electron neutrinos. This is where you get features of the explosion. There's a so-called feature called a slosh. It's a kind of sloshing mode called SASI, standing increasing shock and stability. It's also where an explosion happens, which may imprint itself on the neutrino signal, that information of when the star actually blows up. If it doesn't blow up and turns into a black hole, the neutrino emission may cut off at this point. That would actually be a really awesome signature to see. And then in this last plot here, you can see the cooling. This is where the star emits the, basically cools and emits all its mining energy in the form of neutrinos of all flavors. It's actually in the form of neutrino antineutrino pairs. So, and you get approximately equal luminosity in all the flavors. And so the luminosity then decreases over time, and here's the average energies of them. They get more and more similar between the flavors. So these plots are an example of the information that we're trying to get at in the detectors. There's a generic feature, and this is not, some of the recent models don't have this as robust as maybe shown here, is that the electron flavor is the coolest. The electron antineutrinos are a little hotter, and the other flavors are hotter yet. And the physics reason for that is that the deeper you go into the star, the fewer interactions you have with a neutron star, the deeper the neutrino sphere, basically the sphere of the radius of last scattering of the neutrinos, at which the neutrinos are free to propagate to infinity. That's called the neutrino sphere. The deeper that neutrino sphere, the hotter the neutrinos that come out. And so electron neutrinos have the most interactions with the matter, which is mostly lots of neutrons in there. You can interact with neutrons, whereas antineutrinos don't. And so those come out in higher radii, and so are cooler, maybe around 12 MeV or so. Antineutrinos come out a little deeper, from a little deeper radius, they're a bit hotter, and then the neutron tails are hotter yet. I can mention here, and I'm not going to go into this in detail, but this is a whole topic in itself, is that neutrinos change their flavor, and there are neutrino flavor oscillations, both the regular kind that we have observed in the sun and the Earth, that we expect to happen, the MSW matter effects, which I haven't talked about, but they're sort of maybe more mundane kind of neutrino interactions, neutrino oscillations. But there's also effects where you have the number density of neutrinos is so high that the neutrinos can actually interact with themselves, which gives you complicated nonlinear effects, also known collectively as collective oscillations, and there's a whole phenomenology of that, which can modify the spectrum in non-trivial ways, but usually at somewhat later times. This is a kind of cartoon of what a neutrino spectrum would look like. It's a Fermi-Dirac-like so-called pitched Fermi spectrum. This is the Gaussian parameterization. You can describe reasonably well the spectra in this form with these three parameters, basically the luminosity, the average energy, and this parameter alpha, which is known as the pinching parameter, which will suppress the tail with respect to a regular Fermi-Dirac, at both ends. This is what we often use to describe the spectra, also parameters changing as a function of time. This is a picture in 2 dimensions for one particular model. This is the so-called Gaussian model, one of the ones that is shown up in the literature a lot. Here again, it's these 3 same time scales. So this is the first 80 milliseconds or so after the core collapse. This is the first bit more than half a second. This is 10 seconds. This is one of these plots shows here the time and the energy. So here you see also how the spectrum changes as a function of time in these three eras here. The top plot in pink is for electron neutrinos, and so here you can see this bright flash here of electron neutrinos. This is electron antineutrinos here, so it's got a kind of similar structure except the neutronization burst is emitted, and then this is for the other flavors, which I'll call mu x, which is the sum of all the other flavors. And so this is kind of the truth that we're trying to get to for our measurements. Let me just take a brief diversion to mention supernova 1987A. This is a famous supernova that happened just outside of our galaxy, at about 55 kiloparsecs from Earth. The center of the galaxy is about 10 kiloparsecs away. And we saw a couple dozen neutrino interactions. Here they are, they're some famous ones. They were actually seen about 2.5 hours before the first light of the supernova, actually not from when it was actually observed by humans, but when humans could have seen it. That was basically the predicted first light. The actual first observations were a little bit later than that. And so this is what the events, the interactions that were observed look like. They were almost all Louis bar. They were almost certainly, we don't know exactly what they are, but they're almost certainly all Louis bar, and you'll see why in a bit, and these two water Cherenkov detectors. This one was this was 3 kilotons, this was I think about 8 kilotons, and you can see the pattern is more or less what was expected. It's over about 10 seconds with energies of a few 10 maybe. These different detectors had different thresholds. But this is completely consistent with the basic model of core collapse, of the neutrino emission that would come from core collapse. However, it was only a couple dozen events. There were many more papers written than events, but there's only so much information you can squeeze from this small statistics signal. So there's many, many more questions that would be answered by having a high statistics supernova neutrino observation. And, yeah.
I have a question.
Yeah.
Is it grouped into 3 because of the 3 mass cycling states? Or
probably not. It's probably just statistics.
Okay.
Yeah.
Suppose you
No, it's definitely, I should say definitely not because of mass eigenstates, because the delays of the different mass eigenstates are shorter than that interval. But it's probably just populated by statistics. It's consistent with just sampling statistically. There are other ideas that could come up from, people have come up with ideas for example, these later ones, which are at lower energy, but there's no strong indication there's anything different from statistics here. Okay, and here is the anniversary of this was not very long ago, and a year and a half ago. These are colleagues singing happy birthday to a supernova, actually wasn't there. Pictures. So, what can we learn? And here's just a summary. There's actually 2 classes of knowledge that we could get from observing the neutrinos from the next nearby meaning in our galaxy and beyond, the next supernova burst. One category is astrophysics, basically, the core class physics. We will learn about the explosion mechanism. You can actually see what's happening deep inside the star. We'll learn about the explosion mechanism, how the protoneutron star cools. There's also possibly exotic matter formation will give you signatures. If a black hole forms, that would be very dramatic and exciting. You would actually see a sharp cutoff of the neutrino luminosity after a second or so. So that would be a very dramatic signal, and it would actually be very interesting to correlate that or not with an optical observation or electromagnetic observation. You can see about dynamics happening in the star. There's also information to be had about nucleosynthesis in the supernova from the neutrino flux. Now, on the particle physics side, neutrino absolute mass is actually, at the time of 87A, the world's best limits on absolute mass from the spread of a signal. So what neutrinos having an absolute mass does for you is you will get a mass and energy dependent delay, and so a burst that originally has a narrow spectrum will get spread out. However, at the time, actually, the limits that were made from that 87A observation were actually competitive with other limits was a few tens of eV for absolute neutrino mass. However, this, what we are likely to get from the next supernova is no longer competitive with terrestrial absolute mass experiments like Catrin. But still, there's potential information to be had. We can learn about neutrino mixing, about oscillations. Flavor conversion in the supernova and the Earth will imprint signatures on the spectra of flavor as a function of time. And there's also other neutrino properties. You can set limits on exotic physics from the energetics of the explosion. Many limits already from 87A that we can improve with the next supernova. And this is kind of a virtuous circle in that the more input there is from other observations in photons and gravitational waves, in fact, will help to constrain the astrophysics to enable better inference of neutrino properties. And vice versa, as there's an entire terrestrial neutrino physics program that will improve knowledge of neutrino properties that will only enhance the information that comes out from the astrophysics. So it's a collaborative kind of thing. And the information from the neutrinos is in the flavor and the energy and the time structure of the boost. There's one more thing, which I'll mention briefly at the end, is you also get an early alert. The neutrinos are first, and they enable a warning to astronomers that something is about to happen. I'll tell you a little bit about how well you can actually point. It turns out that it's not the greatest, but it's not nothing. And that's another benefit of observing a supernova in neutrinos. So what do you want in a detector? So the information, as I've already said several times, is in energy, flavors, and time, so you want to be able to gather as much of that information as you possibly can. And so here's the wish list now for a supernova neutrino detector. And what you want is as large a detector as possible. So some of those of you who did the exercise in the tutorial know that you want lots of targets. So you want large detectors. And the back of the envelope for supernova is if you want 100 events, you need about a kiloton of detector mass. It depends exactly on the material and so on, but it's about a kiloton. If the supernova is at 10 kiloparsecs, 10 kiloparsecs is a little bit beyond the center of the galaxy, and it's our kind of benchmark distance for a typical galactic supernova. And of course, it improves if you get closer by the distance squared, and it gets worse as you go away. You want low energy threshold. You want thresholds of a few MeV or better. Most of the events are going to be around 10-ish MeV or a few tens of MeV. You want energy resolution. You want to be able to measure the spectrum. You want to be able to resolve features in it. You want angular resolution. If possible, you want to be able to point back to where the supernova is. And their nature is not terribly kind in that most supernova neutrino interactions are not very directional. So they forget the product you get out, forgets its parent, forgets where it came from. But some of them are directional, and I'll say a bit more about that. You want timing resolution, certainly much better than seconds. You want to be able to follow the time evolution. And you want low background, even though these events come in a burst, if you're on the surface in a sea of cosmic rays, even a big burst of neutrinos may not show up. Cosmic rays, you've got about 1 muon per second going through your hand. You can imagine, even if you've got 100 events in a kiloton, that could swamp you. And radioactivity and all that kind of stuff you don't have to worry about. So usually these detectors are sited underground in order to get away from cosmic rays. The surface detectors may still be sensitive if you know when the burst is happening. The one I've highlighted here, which is really important for the physics, is you want to be able to tag the flavor components, by which I mean if you get a neutrino interaction, you want to know what flavor it came from. You want to know what the flavor of neutrino was that created that particle. And that experimentally is actually can be relatively challenging. And then you want to have high uptime and longevity, just because these events only happen every 30 years or so, optimistically. And so, some people, that's a problem, they don't want to wait that long. But what I think that means is we better be ready to gather as much information as possible when a supernova happens. But this low frequency of actual supernovas means that most of the detectors I'm going to talk about are actually not built only for supernova neutrino physics. They're also built for, they have a day job to do oscillation physics or other things. of interactions with neutrinos that are important in this 10 MeV range, where you get supernova neutrinos, so maybe a few to a few times of MeV. So you have elastic scattering on electrons, and that, I think that was the first tutorial problem on calculating supernova neutrino interactions with electrons in your body. That's actually quite a low cross-section, relatively speaking, but everything's got electrons. It will happen in any material. It happens in a charged current and a neutral current way. You can change to make a W or a Z with an electron if you're a neutrino. This is, even though it actually is typically a real low rate, it's actually significant for supernova neutrino detection because it's directional. Because the electrons are light, they get kicked forward, they remember where the neutrinos came from, and if you can measure the direction of the electron, you can point back potentially to where the supernova is. Then you have protons, also simple targets, and the relevant interactions here, this is actually a very important one in general, inverse beta decay. I alluded to it in the first talk. This is an electron antineutrino interacting with a proton, a free proton, in, for example, water or hydrocarbon. And what you get is a positron, which is a charged particle that you can see in your detector, and a neutron. And if you have the right detector, you can also see the capture of the neutron on something. Some materials, when they capture neutrons, they will spit out a bunch of gamma rays, which is also something that is potentially observable. And the positron will also annihilate. You can also potentially see that. So this is actually potentially, even though it's a simple interaction, a rich final state in terms of its taggability. You can also have elastic scattering on protons, where its cross-section is also relatively high, and you get a recoil proton. So maybe this one is like scattering with a bowling ball, and you have to see the recoil of that proton, which can be experimentally challenging, but it's possible. And this is neutral current, so it's sensitive to all the flavors. And then you have interactions with nuclei, which I spent some time talking about generically in the first lecture. You can have charge current interactions of electrons on the nuclei. You can get either electrons or positrons, depending on whether it's a neutrino or an antineutrino. And you can also get other final states. You can other particles in the final state. The nucleus can kick out, can spit out a neutron or a proton, which potentially you can see. You can also get gamma rays and other stuff. Then by neutral current, you can also have an inelastic excitation, where the neutrino kicks the nucleus into some excited state, and then you can see the subsequent gamma excitation. Or you can have sevens, which I talked about at the end of the last lecture, where this is maybe if this is hitting a bowling ball with a ping pong ball. This is hitting a boulder with a ping pong ball. It's a very high rate, but as I emphasized in the previous lecture, very low energy recoils and can be quite difficult to see. And I'm highlighting this one because this is actually the one that for the existing large detectors, this one strongly dominates the signal that you can see. It's basically UE bar. Okay, cross-sections in this energy range. Here's an example of a bunch of cross-sections. It's a bit of a forest here. What you see down here is elastic scattering on electrons. Somebody asked me about oxygen. If you're actually calculating the number of solar neutrinos that interact in your body, and you want to consider more than electrons, and we look at oxygen, and so here you can read off the cross-section here for interactions on oxygen. Actually, you probably wouldn't get that many here because of the threshold. So it's actually probably fairly comparable cross-section. This is cross-section per target. You get fewer oxygens per water than for electrons. But then there's, these are other interactions here, and the coherent scattering is the highest. But I want to point out here that experimental measurements of these interactions are very, very sparse. So we understand theoretically, very cleanly, elastic scattering on electrons and on protons, and inverse charge current scattering on protons. That's very clean theoretically. Those are simple targets. But other nuclei, there's very poor information. There's been very little measurement, very few measurements on a few targets, and those measurements that exist are not very precise. Okay, now just want to make a point here about interaction thresholds. This is a log scale in X. These plots here are the spectra that you expect. These are the quasi-Fermi-Dirac kind of spectra from the three different flavors. And here, these vertical lines are thresholds for different interactions. So if you want to see inverse beta decay, moving bar and proton, the threshold for that is something like 1.8 MeV. And so any neutrinos that have energies below that, you will just not see at all. This is a charge current scattering on argon, has a higher cross section. This is scattering on oxygen, which has an even higher threshold, and so you only can see this part of the spectrum above it. Elastic scattering has no threshold, so that's good. You can see the entire spectrum. But if you want to see muon neutrinos in charge current interactions, if you actually want to see a muon pop out of that interaction, tethering the neutrino as a muon neutrino, if you want to explicitly see muon flavor, you need more than 100 MeV of neutrino energy. And you can see from this that the entire supernova spectrum is less than that. And so you cannot see charge current muon neutrino interactions. You know, maybe there's a tiny tail, but basically you can't see it. And so the only way you can see muon and tau component of the flux, which is 2/3 of it, is through neutral current interactions. And you can't tell the difference between the flavors. Okay? And so that is an important concept for supernova neutrino detection, and that's why I divide these things into three flavors, why everybody does it. You've got the nuis, the nui bars, and the nu x's, which are the three observable categories of neutrinos. And actually, in the supernova also, because energies are such that charge current, it's really, there's no charge current interaction with muons, muon neutrinos, they're all degenerate. The nu's and taus are basically all the same flux coming out of the supernova. There's small differences, but it's basically the same. So that's why nu x is all of these together. Okay, so here are the main categories of supernova neutrino detector types. There are some made of water, either liquid or solid. There's hydrocarbon, usually liquid, scintillator. There's argon, usually in liquid form, and then there's lead, and there's some others I'm going to talk about briefly as well. So I'm going to go through each of these categories. So first I'm going to start with Bobby-Cherenkov detectors. So this is where inverse beta decay, good old inverse beta decay, is really dominant. Water has lots of free protons. This is a reasonably high cross-section for that. What you see in a water detector is the positron's Cherenkov light. So the positron, when it goes faster than the speed of light in water, when it goes faster than c over n, it makes a shock wave of light, which you can detect. It's actually quite weak light. It's pretty faint, but you can detect it with single photoelectron detectors, photomultiplier tubes, and the canonical configuration is a volume of ultrapure water with the inner surface covered in light sensors, usually photomultiplier tubes. Positron that comes out of this interaction is almost isotropic. It has almost forgotten where its parent came from. And so you can't really use this very easily for pointing. There's some very weak anisotropy, but it's hard. In water, you cannot see the half MeV gammas that come from this positron annihilation. Why not? Those are totally invisible. Why can't you see those? Anybody remember? I said it in the first lecture. What's that? The threshold, the Cherenkov threshold. They're not going faster than this. You can't. The threshold is about an MeV, and the way you see gammas is actually they Compton scatter on electrons, and you see the scattering electrons, okay, in this energy range. And you're never going to see those by Cherenkov light. I'll say a little bit about neutron detection in just a second. And these tend to be limited in their thresholds. The threshold's typically around a few MeV for actually seeing an interaction, not for the interaction to happen, but for actually observing the interaction. They're limited by the light sensing capability. So Super K has about 40% photo coverage and gets about 6 photoelectrons, photons converted to observable pulses, per MeV that can be possible, which actually is quite low compared to some other scintillator detectors, which I'll talk about in a second. So this is really the only current instance of a large water Cherenkov detector. It's in Japan, famous also for neutrino oscillations and total neutrinos and proton decay searches and many other things. Supernova neutrinos is not really its day job, although it does a fabulous job. It will do a fabulous job if a supernova happens. This has 50 kilotons total of ultra-pure water. The inner surface of the cylinder, which is 40 meters high and 17-meter radius, is covered in photomultiplier tubes, which are about that big. There's 13,000 of them on the inner surface and about 2,000 of them looking outwards. The point of this outer region with the outward-looking phototubes is to remove cosmic rays. Even underground, we get about 3 cosmic rays per second going through Super K. This is where we eat lunch here. This is drive-in. This is what you get in a water transfer detector. This is a plot of the observed spectrum, the expected spectrum as a function of the observed energy in 100 kilotons of water. This is actually a plot from Burghausen when we're thinking about a 100 kiloton detector. But to take away from this plot here, so these are different channels of interactions. The inverse beta decay is black, and you can see that this is very much dominated by inverse beta decay. So water Cherenkov detectors are really new E-bar detectors. They're sensitive to the inverse beta decay. And that's why, when I showed you 87A, we're pretty sure those are almost all electron antineutrinos. These detectors are, that's what these detectors are sensitive to. There's other channels, but they're very much subdominant. And what you could do in a detector like this is you could map out events versus time. You could actually distinguish between models by, if you have huge statistics, Super K will see something like 8,000 events, and a supernova at the center of the galaxy. You can see many, you can see, really map out the structure in time with good statistics. Another interesting thing about water Cherenkov detectors is that even though the elastic scattering of electrons, even though that's a very small cross-section, relative to inverse beta decay, it's maybe a few percent of the events. It is a directional interaction, and what that means is that you can actually use it to point back to the supernova. In fact, Super K is really the only current detector that can do something like this. And so the electron is scattered forward. This is approximately the pointingness of it. It's within about a 30-degree angle, and so you can then tell the direction roughly to about 30 degrees over square root n, where n is the point you see. This is the kind of picture on the sky that you can see. This is a picture from Georg here, where it's cheating a bit because he's showing here the elastic scattering interactions in a different color, but in real life we won't easily be able to tell those color. We won't be able to tell those fractions apart. It would be nice. We actually do have ways of doing it. So it is somewhat degraded with respect to that. This is a Super K paper. This is showing you actually the same thing, where here's where the direction is, and you can kind of see with your eye that there is an excess here. There's kind of a more filled-in region here, and you can actually fit and find that direction. And this is just an example of how well you can do for different supernova models and as a function of distance. And the answer is something like 5 to 10 degrees would be a realistic evaluation of the direction to the supernova in Super K, which is certainly better than nothing. Some astronomers will sneer at that, but any information is better than that. And here's an animation. This was made by Speed and Oakline. This is a Super K event display in unrolled view. So this is the cylinder unwrapped. And each little dot is a photomultiplier tube, and the color tells you how much light you received. And so I'm going to click it, and this is actually real time. This is what it would look like including background in Super K. And this inset is the outer detector, which shouldn't be seen very much in this. So here I'm going to click on this. There it goes, bam, there it goes. So there you can see the supernova neutrinos and their fits, and the direction here, filling up here, and this is the. Now it's all over in 10 seconds. Actually, I think this is 20 seconds. Okay, so let me now make a comment about neutron tagging. So this is the inverse beta decay interaction, and it makes a neutron. And if you can actually detect that neutron, you tag the interaction as new E bar, okay, to some reasonable quality. And this is actually, I'm not going to talk about the diffuse flux. That's going to be very useful for finding neutrinos in that diffuse flux. But for bursts, it's actually really useful for disentangling flavors. We know which events, event by event, are Newey bar and which are, for example, elastic scattering. So this, in fact, can help the pointing by getting rid of that isotropic background. Now, in Super K, this is what I call drug-free neutron tagging. We can actually sometimes see, with relatively low efficiency, but we can sometimes see the neutron captured on a proton, which makes a deuteron and gives a 2.2 MeV gamma. And that is a challenging thing to see in Super K because our threshold is really more like 4 MeV. We don't see very much below it. But with some new electronics and some strategies for going after this, we're able to get about a 20% tagging efficiency, just with nothing in the detector. This is the drug-free strategy. Now, just as in sports, in Super K, the performance is enhanced by doping. And so if you actually dope the water with something, and what we were actually using is gadolinium, you can dope the water with something that has a higher cross-section, a higher probability of gobbling neutrons and spitting out something that you can observe so that you can tag the neutrons and tag the intermediate decay events. So if you see a positron Terran covering accompanied by a bunch of gammas, which will make a little diffuse cloud within a capture time of about 20 microseconds, then you know you have an intermediate decay event. And gadolinium, when it gobbles a neutron, will spit out about 8 MeVs worth of gammas, of which you can see about half from Compton scattering in the water. And so this was extensively tested, and Super K is now officially going ahead in a new phase called SKGB, and the work is happening this summer. This is the schedule that was shown at Neutrino 2018. I got an email this morning that said that the tank is actually now completely drained, except for some little pockets of water on the bottom. This is the schedule, so the tank is being drained this summer, phototubes are being replaced, the bad ones are being replaced. It will be refilled with normal water, and then next year, the first gadolinium at low concentration will go in. And then if that works well, there'll be, at some later time, a larger concentration of gadolinium, and Super K will be in its new phase of SKGB. And this is just a nice picture from the upgrade. I do want to point out that because of this, it is absolutely forbidden to have a core collapse for the next at least 4 months, and preferably longer. So I just want to make that clear. So I just want to tell the generators of galaxy crews, you must hold it in. Okay, so next generation water. There's one big thing on the slate, which is Hyper K, which is effectively an upgrade of Super K. It's new detectors of Super K, where the nominal design is a total of 374 kilotons divided into 2 modules. Right now, actually things are firming up. These would be enormously, basically the same idea, but even with lower threshold, better efficiency, and larger statistics. And for core collapse supernova in the galaxy, it could be as much as 100,000 events. So really enormous statistics. Mostly electron neutrinos, but this is actually getting to the statistics where the subdominant channels are actually reasonable things to go after. And then there's another kind of water Cherenkov detector, which is what I call the long string water Cherenkov detector. And these are long strings of light sensors deployed in water or ice. And their day job, their nominal purpose is actually to look for very high energy neutrinos. In fact, they've had spectacular success in that recently, where they're very sparse arrays, and they're looking for enormous tracks depositing lots and lots of energy up to PeV, EeV kind of things. And you think, well, how can these things actually see little supernova neutrino events, which are just little tracks maybe that big? And the answer is, what they can do is they can do it statistically. If a supernova happens, there are enough interactions in the water or ice that the ice effectively glows with excess photons from the Cherenkov light of these inverse beta decays, that the photosensors can pick up the statistical excess of light. And so they can't see individual events, they can't reconstruct individual neutrinos, but they can statistically map out the time structure. This can actually be done quite impressively. This is an example. This is the kind of excess that they can map out over a supernova burst up to about 3 seconds. And this is the kind of map of origins of the photons that they would see in the current ice cube configuration. And things like KM3 net and Antares also should be sensitive, although they're more subject to noise in ocean water with respect to ice. Okay, let me talk about scintillation detectors. These are also inverse beta decay detectors. They are also sensitive to millibar. They have lots of free protons. They have an advantage with respect to water in that you get typically much more light. There tends to be maybe tens of times more photons for energy deposition. You get much brighter flashes in scintillator than you do in water. However, the disadvantage is that the light that's emitted is isotropic. You just get these sort of blurry glows. You don't get nice Cherenkov rings where you can, unless you carefully craft your scintillator, normal scintillator, you just get kind of fuzzy blobs rather than crisp rings, relatively crisp rings. And so, but this is very popular technology. There are many examples of current and future detectors worldwide, mostly of the up to kiloton scale of these. So here's just a little more detail. It's hydrocarbon, so it's carbon and CnH2n is the nominal formula of this. Also the same kind of, they're usually the same kind of thing where you have a volume that's surrounded by an inner surface by multiplier cubes. Because of the large light yield, you can have very low thresholds and also good energy resolution. And you can also, these have also often been doped with gadolinium for the same reason. And so this is much better. You don't really need to dope as much in order to get, although some of you do, to get the capture of the neutron, to tag an inverse beta decay event. And this is a cartoony kind of plot of the interactions you would get in scintillator. And again, you can see the thing to notice on this plot, this is the spectrum of observed energy. The total here is the pink, and the black is inverse beta decay, which is very much dominant. This interesting spike is actually a neutral current channel, which would be actually very nice to see the total energy of the supernova. Here's, yeah?
Why do you have that version on carbon?
Why do I have the? That is for the neutral current channel. Actually, you can get, and this is actually one of the few measured interactions. It's so it doesn't care about the flavor. It's an excitation of the carbon nucleus that gives you a de-excitation of a 15 MeV gamma. And so this plot would be made in the assumption that you can contain those gammas and capture their energy, which actually is excited state of carbon. Yep. And that Karman experiment has actually measured that cross section. Okay, so here's the rogues gallery of current and near future scintillator detectors. There's Gamma in Japan, 2 kiloton. There's a segmented detector called LBD in Italy. Borexino, 1/3 of a kiloton in Italy. Famous for solar neutrino detectors detection. Snow Plus is, I think, currently filled with water, but will have scintillator. Is in Canada. Is actually going to do double beta decay, but will still be sensitive for supernova. And then NOVA is a surface detector, which has a lot of background and still should be able to extract some supernova neutrinos. These are future detector proposals. There's Juno in China, 20 kilotons, 2 kiloton detector also proposed in a different place in China at Jinping Laboratory. And then this is conceptual. It's a detector called Thea, which would be very large, and they're looking at scintillator where you could actually get both Cherenkov and scintillation signal. I think also Jinping is thinking about that as well. Okay, now let me talk about argon, which is actually what I've been personally working on most of my time on supernova neutrinos these days. And so liquid argon time projection chambers are detectors that also have a day job of looking at high energy events. This is the day job is for long baseline oscillations. And these have in principle, really exquisite tracking capability. The idea is a time projection chamber idea where you have a particle that leaves an ionization track. you put a high electric field on it and you drift the ionized charge until it reaches an anode plane, and you pick up that charge to get a two-dimensional projection image of the track, and you use the time of the drift to give you the third dimension. So you get a three-dimensional image digitized of a track. And so that has been used in many, many contexts. It's a really attractive technology. For supernova neutrinos, what you're doing then is tracking 10 MeV tracks, which tend to be something of this size that you could hold in your hand, as opposed to the high energy neutrinos from a beam, which would be more meter-ish scale. There are many instances of this kind of detector. There's Icarus, which ran in Italy for a while at Gran Sasso, obviously with high energy threshold. It has just been moved to the US. Microboon is on the surface, is in the US, should have sensitivity to supernova neutrinos. SBND is a future experiment in the US. These detectors' day jobs are short baseline oscillations. And then there's Dune in the US, which will be humongous, a 40 kiloton detector. And so what you're after here for liquid argon is this is the dominant channel here, which is charge current interactions on argon nucleus, where the observable here is primarily the electron that comes out of the charge current interaction, which you track. You actually see the track in a liquid argon time projection chamber. And then you have an excited state of potassium, which gives you gammas, which in principle you can see the Compton scatters in the detector as well. There is a channel of inverse on antineutrinos. There's less information that's improving about neutral current excitations, and there will also be elastic scattering of electrons, although at a lower threshold, and you can use that in principle for pointing just as for Cherenkov detectors, except that your pointing mechanism is by actually tracking the electron. Here are the cross sections in argon. This is actually the plot that you can use for your tutorial if you can go back to it or if you're doing it later. So this cross section here as a function of neutrino energy, so this is the regime for a supernova of a few tens of MeV. This cross section here is much larger than the other ones. This is nu-E charge current on argon. So this is the one that will be dominant in argon in most of the events. And this is an example. This is no oscillations. I'll show you what happens when you assume some neutrino oscillations in a second. This is the flavor composition of your interactions as a function of time, or interaction channel composition, as a function of time for a particular model. This is the so-called Gaussian model. And so here, this is a log time. You see this, you get tens of events in the neutronization burst. That would be actually really, really cool to see that. Then this is the accretion period, and then cool, this is for non-uniform bins. This is the energy spectra, again, in a stacked plot as a function of observed energy. So it peaks around 15 and goes all the way up to maybe 40. And I just want to point out that neutronization burst, which looks so attractive and lovely, it turns out that physics may kill it, but interesting physics may kill it in an interesting way. If you assume neutrinos oscillate in the supernova and they are affected by the matter effects, which I haven't talked about, but it should be fairly robust at early times, what you get is a strong suppression of the neutronization burst. You get the electron neutrinos converted into other flavors that are not as easily observable. And so here is the example here for you have no oscillations, and we know that's not true. We actually know that's not what nature does. Here's the neutronization burst. If the hierarchy is inverted, you get a suppressed burst, and you get a really suppressed burst if it is normal. And in fact, you also get, assuming the MSW oscillation is good, you also get a different event rate in later times. So this is actually a fairly robust mass order signature, whether the neutronization burst is a little bit reduced or whether it's strongly reduced. And the instance of this large detector I just say a little bit more about is Dune, deep underground neutrino experiment. It's a big project in the US. The day job is the long baseline oscillations where there's neutrinos sent over 1,000 kilometers, more than 1,000 kilometers from Fermilab to South Dakota. Supernova burst is, although it's maybe not the day job, is in the list of primary physics goals. And so it's an important feature, important activity that I'm personally working on to make sure that Dune is sensitive to supernova burst. neutrinos that is really both designed and dedicated to doing supernova neutrinos only, and it was actually made out of leftovers, made out of recycled material. It was not expensive at all. And this exploits interactions, both charge current and neutral current on lead, where what you get for a final state is you get a de-excitation of the nucleus. When you have an extra neutron in lead, it doesn't hang on to it very well, and you can get either 1 or 2 neutrons spit out. And what this detector did is took leftover neutron detectors from the old SNOW experiment and put them together with some leftover lead from the old cosmic ray detector, and has a detector that should see a few dozen events from a center of galaxy supernova. And there's information in the relative rates of singles and doubles. And this is just a little zoom in on the neutron detectors. These came from SNOW. They're helium-3 counters where what you see is the charge signal from a capture of a helium, a neutron on a data. Okay, and now let me say a little bit about supernova, the same thing I talked about this morning, sevens, but in the context of supernova neutrinos. This is the same slide I showed you before. I want to just point out this is neutral current. It doesn't care about the flavor of the neutrino. And that matters if you want to detect supernova neutrinos, because it's the only way you can get at 2/3 of the flux. And so you can get at the entire energy of the supernova using neutral current interactions. And there are now dark matter detectors which are sensitive to supernova bursts via sevens. Now dark matter detectors are getting big enough that they would actually see a substantial number of events. You get a handful of sevens interactions per ton of detector material. So here we're talking ton detectors rather than kilotons. These are very sensitive detectors, and so it's very hard to scale them up, but they are now getting to tons or multiple ton scale. And this one here, called Darwin, is a vision for a proposed next generation detector. So these ones are all xenon based that are, there's xenon and there's LZ. And they are, so xenon is a few ton scale, xenon n ton, 7 tons, and then Darwin, and LZ is also 7 tons, and then Darwin and Vision is something like 40 tons. Yeah. And so this is the kind of thing you would be able to see in these kind of detectors, and the significance of detection, you can see it's actually really pretty reasonable out to LMC for something like Darwin. And these are also very quiet detectors. They're looking for very, very rare signals, so really very low background. And the kind of things you can learn, this is just an example from this nice paper, where here, these are these different detector configurations of successively larger masses, where the biggest one is Darwin. This is how well they would be able to measure the total energy from the supernova emitted into neutrinos. And this is how one could constrain parameters of the supernova. This is average neutrino energy and neutrino flux amplitude. And this is what some people were mentioning before. This is the so-called neutrino floor for dark matter experiments for sevens. And so this is a parameter space for WIMPs. This is the kind of thing that WIMP people have on their t-shirts. This is the mass of the WIMP, and this is the cross-section. And what these experiments can do if they see no signal is constrain some region above that line. And these detectors now, they're getting big enough that they're going to get to the point where sevens coming from natural neutrinos like the sun is actually going to interfere with the, it's going to create background for WIMPs. And so this solar neutrino shoulder is the so-called neutrino floor that the first of these dark matter experiments will start to run into. In this region, the supernova burst flux, when it happens at 10 kiloparsecs, is 9 to 10 orders of magnitude greater than the DSMB flux. So this is diffuse supernova neutrinos that's creating this background floor here. But if you have a burst, you have an enormous signal there, which you can think of it as basically the neutrino floor coming up to smack you in the face. That's what would happen if you have a supernova burst. Okay, here's my big summary table. You don't have to look at the details of this. I just want to give you the impression there's a bunch of detectors. The purple ones are online now and sensitive to supernova neutrinos. The green ones are recently turned on. The yellow ones are in the future, but some of them not so far away. And these are example signals in the big detectors in water and argon and scintillator. And here you can see these different lines correspond to different models, and you can see that there's clearly a structure to be measured there. And just to show again the neutrionization burst, this is the same signature I showed before in argon. It was very clean. There's also information in the other detectors, especially in the slightly later eras. And another summary of how many you'll see, and often a question as well, what do you get from Andromeda? So it just goes down as 1 over r squared. This is all that's in this plot. This is for these different detectors. The center of the galaxy is here, or edge of the galaxy is here. Andromeda is here, so if you read this off, you can see that for super K, you might get like 1 event from Andromeda. For hyper K, you could get a dozen, so it could be like 87A from Andromeda if there was supernova happening in Andromeda. And I also want to make the point that unlike the long baseline experiments and the different continents which are competing with each other, this is not that situation. The more information we get worldwide, the better off we are. It's really a good thing. You want everybody to gather as much information as you possibly can. You want all the flavors, you want all the signals. It's really it's a collaborative kind of thing, not competitive. And now let me mention just very briefly the supernova early warning system. This is the exploiting the fact that neutrinos give you an early warning that a supernova is going to happen. The pointing may be limited, but there may be some from super K in our current configuration, and maybe that will improve as more detectors come online. This has been running smoothly since 2005, so about 13 years now. We have not seen any supernovae, none that happen as far as we know. It involves currently all 7 of the supernova-sensitive detectors worldwide. And this is a comment I've made before in talks. I just want to make this comment again here, a sociological comment. There's something of a cultural clash between astronomers and neutrino physicists sometimes. So everybody's hungry for data, and you can have something astronomical that happens 10,000 times a day, or you can have something really big that happens once a century. You get one giant worm, or you can get lots of tiny worms. This is in extremely arbitrary units. Made it up. This is the importance of catching every little bit of data. So if something happens 10,000 times a day, you don't have to worry about it so much. But if you get one really big worm, you really want to get that one. Unfortunately, the level of sustained human interest sort of looks like this. That you get kind of bored if you get it 10,000 times a day, but you also get bored of waiting if it only happens once a century. And so that's a bit of a mismatch, and it's very important that we don't, close this gap. We make sure we're ready to see everything. And the neutrinos are coming. The far side of the Milky Way is 750 light centuries away. That means that 2,000 core collapses have happened already, because it will take 650 light centuries to see them all, but they're on their way, they're coming. This is where we are. These dots are the historically observed, the processor is historically observable ones, but we are now sensitive really to everything with neutrinos even behind the dust. And actually the other instrumentation. Okay, so I probably don't have time for this, so I'll skip this. Let's go to the takeaway messages. There's huge information to be had from core collapse burst. We need the energy, the flavor, and the time. We have very good sensitivity with current and near future detectors. There's an early alert network, a good time for IceCube. We're still mostly sensitive to UV bar. This is Dorothy in Kansas looking for a supernova. And I just want to point out that future detectors will have huge statistics, much richer flavor sensitivity, and Dorothy is much more likely to see a colorful supernova in the future than even now. So I will stop there.
Other questions for Kate? I have one. So maybe you said it, but what is the thing of hypercamia?
So I think it's, I'm actually not a member of Hyperconic, but as I understand it, it has R&D funds right now, and there's no decision yet on whether it will go ahead. But there's R&D going on.
No decision.
It's all theoretical rather than technical. There's no technical obstacles, but yeah.
there another question? Not for the moment, so we have another short coffee break. Ah, there was one. Sorry. Yes.
Can you just say again, I think you have it on one of your slides, but so the difference between the normal and inverted order would be bursts, right?
Yeah, so there's actually multiple signatures of that, and I just picked one which is maybe the most robust.
Okay.
So the collective oscillations, the neutrino interactions in the supernova kind of mess things up later, after the initial neutronization burst. And there actually are mass ordering signatures in that, but I think there's more uncertainties down than you actually expect. Right at the very early part of the supernova in the neutronization burst is more likely to be just a simple neutrino matter effect that would give you either a suppression, a strong suppression, or a weak one, depending on the hierarchy. Yeah. So this is probably the simplest and most robust signature. But there's lots of other effects on the supernova as well, on the flux that you would expect, depending on the hierarchy. There can be shockwave dependent effects. There's more things than just this. I mean, in fact, you can see at little later times, this is assuming it's still simple MSW oscillations. There's also a faster turn on for the different kinds of detectors, depending on the hierarchy. I should say ordering, not hierarchy. Some people yell at you if you say hierarchy.
Another one? Okay, before we break, there's another short coffee break. Maybe you can be back by 5:15. The usual place, there should be some coffee and refreshments left from the other coffee break. So I'll see you back for the next lecture in 15 minutes. Thanks a lot.